One of the central tools in probability is what's called expectation. And in this video, we'll start to take a look at expectation for discrete random variables. Discrete random variables. So intuitively, you can think of expectation as sort of the average value of something. You're averaging over some probability distribution. So since we're working with discrete random variables, let me introduce a little convenient notation. I'm going to use this capital script X with a line through it to denote the range, or rather the image of omega under the function x, where x is a random variable that we're considering. And so the definition of expectation, the expectation, sometimes called the expected value or the mean of a discrete random variable x with PMF lowercase p is, we denote it by capital E of x, and it's the sum over all the values, little x, that x may take, of that value times p of x, times the probability that x takes that value. So you remember, the PMF is, this is just the probability that x equals little x. And this is true when this sum is well defined. I'll put that in quotes since I haven't defined what I mean by well defined, but I will make that precise briefly. And otherwise, if it's not well defined, the expectation does not exist. We say that the expectation does not exist. So that's expectation, and let me give you a very simple example. So an example, so if x is a Bernoulli random variable, if you remember the definition of a Bernoulli with parameter alpha, then x takes values in just the set 0 and 1. And so the expectation is going to be, so we're summing over these values, and then we've got 0 times p of 0 plus 1 times p of 1. And this is, of course, 0, and p of 1 is just alpha by the definition of the PMF for a Bernoulli random variable. So this is just alpha. And one thing to note here, this illustrates the fact that even though this is sometimes called the expected value, it's not necessarily a value that the random variable might ever take. So since this x here, this Bernoulli random variable, only takes the value 0 or 1, but alpha could be like 1/2 or some other number between 0 and 1. So that's just a very simple example. And it would be a good exercise for you to compute the expected value for some of the other discrete random variables like binomial, geometric, and Poisson that I mentioned in the earlier video on discrete random variables. Some of them might be a little tricky. They might require some knowledge of series and evaluating infinite sums. So let me now explain what I mean by this sort of mysterious statement, the mysterious condition, well defined. So let me say well defined. Let me illustrate the problem briefly. So here's a question for you. What if I have an infinite sum of the following form: 1 minus 1 plus 1 minus 1 plus 1, etc. Minus 1, blah, blah, blah. What does this equal? Well, you might say, okay, well, I can group these. I could say, well, 1 minus 1 is 0, plus 1 minus 1 is 0, plus 1 minus 1 is 0. Oh, so that means then the whole thing must be 0. But you might also say, well, this is 1, and then minus 1 plus 1 is 0, minus 1 plus 1 is 0, and so on. So then it would be 1 plus a bunch of zeros, so it would be 1, right? So something's not right here. Something's a little fishy. So basically, what the problem is that this sum is not well defined. Undefined. And so more generally, if we have some sequence of values, a1, a2, etc., real numbers, then we consider the sum as I goes from 1 to infinity of these numbers, we can break it up into two parts. We can break it into the parts where ai is greater or equal to 0, plus the parts where ai is strictly less than 0 of ai. And let's call the first one b and the second one c. So this is b and this is c. And we will say that, so we have this, and we say that this sum is well defined if either b or c is finite. So, for example, here, if we took all the positive parts, 1 plus 1 plus 1, that would be infinite. And all the negative parts, minus 1, minus 1, minus 1, that would be minus infinity. So neither of them would be finite. And so this condition would not be satisfied. On the other hand, if we got rid of all the minus 1s here, then we had 1 plus 1 plus 1, then the positive part, b here, would be infinity, but c would be 0. And so that would be okay. Then it would still be well defined. It would be infinity, but it would be well defined. And likewise, if we just took the negative ones, then it would be minus infinity. But since one of them, since b in that case would be finite, b would be 0, then it would still be well defined. So we allow it to be the sum to be infinite, but it has to be well defined in this sense. So you don't want to have minus infinity plus infinity. That's basically the issue. Okay, so now that we've cleared that up, let me give you an example to illustrate that this actually is a real problem that can come up. So here's an example. So suppose I have, so this is an example that e of x may exist and be infinite. So this would be okay. It would be well defined in this case. So if we let c, this different c, we're going to define a new c to be the sum as k goes from 1 to infinity of 1 over k squared. Now, it's not immediately obvious, maybe. Well, not immediately obvious at all, I guess. But this, in fact, is finite. And in fact, Euler proved that c equals pi squared over 6, but that's not really important for our purposes. The main thing is that this is finite. And we will define, so let p of k equal 1 over c k squared. That's this c here. For k positive integers, 1, 2, 3, etc. So this, it's probably not too hard to see. If we sum all these up, then we get c over c and that's of course just 1. But if we try to compute the expected value of this thing, expected value, remember the definition, so we're going to sum over all the values that x could take, and we're going to take, or in this case it's k, so k times p of k, which is 1 over ck squared. K's cancel. We get 1 over ck. And this, if you are familiar with series, this is infinite. This does not sum to anything finite. So in this case, the expectation of x is infinity. But it's okay. It's still well defined. On the other hand, let me change this slightly. So this is an example that the expectation might not exist. So if we modify this, and so this one was just taking positive integers, if we basically do the same thing but also include some negative integers, so if we say p of k equals 1 over, we have to divide by 2 in order to make it sum to 1 over 2ck squared, and this is for, so I'll write it this way, that if k is an integer, these are the integers, and k is non-zero, and this is anything else, it's going to be 0. Then it may be not too difficult to see. Well, let me just write it briefly here. So then if we try to compute the expected value, then we have the sum over all k, right? We've got this thing, k times p of k, and the problem now, if we break this up into the parts where k is positive, so we have the k's which are positive, and then we've got the k's which are negative. I'm not going to write it all out, but basically what's going to happen is that we get the same thing. This is going to be infinite again, and this is going to be minus infinity because now we're multiplying by k which is negative. So what we end up with is infinity minus infinity, which is a problem. This is not well defined according to our criteria, because neither of them is finite, right? In this case, we had two infinite things. So that illustrates expectation for discrete random variables and some of the things that may go wrong with them, some of the subtleties involved.